Yeah. Hello, everybody. This time, this is the last interactive session for the course material processing, casting, forming, and welding process. So this course we have already discussed. We reached certain up to certain level. We have already discussed that you have already gone through that kind of lectures, and you have solved that kind of problems also related to the the subject we have shared with you. You solve problems, and now maybe this is the part where we can discuss the more detail. If we have any difficulties, any problems to understand a very specific problem associated with this course. You know that this course is basically focused on the very basic understanding of the materials processing. And all type of the materials we cover, metallic, non-metallic, and maybe few cases, very specific type of materials. Now, although you have not already mentioned that there is a very specific questions you want to ask related to this particular course, I have not received any such kind of the request. Therefore, I have prepared my own understanding where there might be having some difficulties to understand the very specific topic. So I'll try to cover up these topics to make it once again explain the more simplified way, such that you'll be able to follow it. So basically, I believe that at this point of time, we are in this the last modules, maybe close to the modules 10, 11, 12. I assume in this way. So at the progress of the courses in that way. So focusing on this particular modules, in very selected topics on that. And of course, every time I say like that, if you are really interested to go in much details about the materials processing, you should go for the wide references I have already mentioned. It's a very selective references, and if you're really interested to know, there's a wide coverage of the subjects are also there. You can follow any one of the references as per your requirement. These cases, but till most of the common questions usually raise are these things. So maybe what type of the question will come into this exam? I think that is the most appropriate course questions from your side. So you simply follow the assignment problem. You solve the assignment problem. You can expect the similar type of the pattern of the question, similar type of the marks will be there associated with this final exam. So all can be kind of the multiple choice type questions, of course, and maybe both theoretical and numerical type of the questions will be there associated with this particular subject. Now I come to this point, the selective topics. I start with this non-conventional processing is the colloidal processing and the casting process. So this is basically known as the slip casting process. This is one of the important manufacturing technology in case of the this kind of ceramic materials we can handle. We can make the different component, the slip casting process. How it works? We use the raw material in the form of a slurry. Slurry means the containing fine clay which is called the aqueous slurry. That is having the very fine clay, which is also known as the slip. So that's why it is called the slip casting process. And this actually is put into some porous medium, basically porous gypsum mold. We put it, and of course follow certain time, maintaining certain concentration of this fine clay with this aqueous solution. And then after certain time, once we can get the certain thickness of is deposited, and maybe after depositing, and it takes particular shape, some kind of the rigidity achieved, then we take it away, and then you follow the other next secondary procedures, that will be simply heating, drying, all this, and then you'll be able to achieve the final product. So this is the way we follow the slip casting process, and the deposition of the clay over the porous medium, gypsum mold, can be accelerated in the different way. One is either you can perform the pressure casting process, vacuum assisted casting process, or centrifugal casting process. In pressure casting process, applying some pressure to the slurry such that deposition can be accelerated. Vacuum also same, apply vacuum to the mold, create some pressure differences, and that will help to increase the deposition rate. And in case of the centrifugal casting, you use the simply centrifuging mechanism to deposit the material over the porous mold. And of course, dense refractories for very kind of the complex shape, depending on the shape of the mold. Very thin wall product maybe can be possible. Large structural refractories can also be possible using this particular slip casting process. So here, if you simply follow the figure, that porous is there, with the mold is there, porous mold is there. Over the porous mold, we put the clay over here and fill it up. And of course, after a certain point of the time, some rigid form, thin film will form also surrounding this porous medium, and remaining slurry you can take it away. And over the time, if you allow more time, the thickness can also improve. Now this thickness, or maybe this depositing over this mold wall, that can be accelerated by either using any kind of the pressure casting, vacuum casting, or the centrifugal casting process. Or if you put too much of time, then it can complete the solid component. So this way the ceramic component is usually made it. But this is not the only procedure to make the complete ceramic components. Once it is done, some rigidity achieved, then you take it for the further processing, just to dry it to make the more rigid that part. So this way we can produce any kind of the ceramic components. Simply use the slip casting process. Similarly, we can follow the tape casting process, which is basically tape casting is a very not exactly complete big product. Rather, we use it the purpose of the coating process. Tape casting is a technique to produce very thin ceramic sheets, and that is from the ceramic slurry. That means for the slurry we produce, and we produce a very thin sheet. Here, how it works: dispersion containing ceramic particles along with the polymer binder, which is coated over a substrate, and it is performed. The liquid dispersion, make the dispersion, deposited and spread over the this thing over the substrate, and subsequently try to solidify it. And once it is make a very thin sheet, making the flat surface, then after that we follow the procedure of the drying and the sintering process, sintering operation. Then it becomes more harder, and we can reach finally the component. So this type of the tape casting process is very well-known technique for producing the membrane made of the ceramic, which is for to manage the ceramic process or to handle the ceramic process. We cannot follow the other conventional casting, which usually you can see the for metallic material. We cannot follow the similar procedure to perform the casting of the ceramic material. So that's why for the ceramic part, either whether coating, ceramic coating, or very thin sheet, or maybe big component. In that cases, we follow either slip casting process, or here it's called the tape casting process. Simple process, but we use it. Now, see, this is the material processing. Material processing, one of the most important is the steel processing, how the steel is manufactured. So that is very important in case of the material processing. So here I'm just little bit covering up that first you understand the very basic understanding of what are the different types of the steel. One is the low carbon steel, medium and high carbon steel. Low carbon steel is the carbon percentage less than 0.3%, and it's the microstructure usually ferrite and the perlite phases are there. If you follow the medium carbon steel, it's a range of the carbon around 0.3 to 0.8%, and it actually form bainite or martensitic structure. And high carbon steel usually more than 0.8% carbon, and it can form the martensitic structure. So that phase usually form the martensitic structure. So therefore, we can see that strength actually increases. We know the martensitic phase is more harder as compared to the ferrite or perlite phase. So therefore, strength is actually increases with increasing the carbon content, but at the same time, the properties like ductility and toughness actually decreases with increasing the carbon content. This is the very general trend. We can understand how the property variation easily happen with respect to the carbon percentage in case of the steel. And plain carbon steel is actually having iron plus carbon, along with these things, very small amount of the phosphorus, sulfur, manganese, silicon. So these are the very small percent of the carbon. It basically try to influence in a different way, but quantity might be very small. But main alloying component for the plain carbon steel is the iron plus carbon, and main alloying is the carbon content is more important here rather than the small amount of the other alloying elements. Now also we see the different kind of the alloy steels also. Alloy steel is in this case the alloying elements are added to the steel. Actually also very small quantity, usually less than 5%, to improve certain specific property. And this actually develop the percentage of the carbon and all alloying element is developed depending upon the after lots of trials, lots of experiments, we can achieve the different kind of the alloy steel. Alloying elements, when it is added to much quantity, and for example, maybe sometimes you can use the up to 20% to produce very specific properties such as corrosion resistant. For example, in case of the steel, stainless steel also, although we are telling this is the stainless steel, carbon percentage is low, but some chromium percentage might be very high in case of the stainless steel, so that it will try to impart the corrosion resistant properties. It means that this very specific element impart certain properties. So that's why there is lots of variants of the steels are available. Different are what main alloying elements for the steels are Mn, silicon, copper, chromium, nickel, molybdenum, tungsten, but different percentage can vary also different way. Overall, understanding that there are very basic type of the steel. We know the HSL, a high strength low alloy steel, micro alloy steel, margin steel, stainless steel, tool steel, silicon steel. These are the very common name of the steels we use our engineering, so many engineering applications. And here we can find out how they are different actually. High strength low alloy steel is basically used structural application, mainly the buildings construction or the bridges construction. We can use the high strength low alloy steel. When you use the micro alloy steels can be used substitutes for the heat treated steel in this micro alloy steel. So very small quantity of alloy steel impart the properties. Margin steel, combination of the very high strength and toughness. Usually most of the metal, when it is improved by the strength is very high, usually toughness is usually low. But in case of the margin steel, a good combination of the high strength and toughness is possible in the margin steel. That is the very basic properties of this particular steel. Similarly, stainless steel, mainly we know the stainless steel because of the very good corrosion resistance properties. And tool steel, we use the cutting tool also, making the die also, the different manufacturing process. But in this case, we need the properties of the tool steel is the very good wear resistance properties, should have very good toughness so that it can absorb the vibratory load, and any kind of and strength can be very high also. All kind of properties combination is used in case of the tool steel. Similarly, silicon steel, which is find more application in case of the electric application and magnetic application, we can use the silicon because very basic properties of the silicon. So therefore, we can see that different composition having different kind of the steels, their applications area are also different. So there are so many variants of the steel are possible, each are having their own advantage as well as the very specific properties able to achieve. Or some cases is of manufacturability of this particular steel might be there. Now, when you come to the iron, we are telling the steel is one side, less than 2% of the carbon, usually known as the steel. But cast iron, which is alloy having more than 2% of the carbon. So that is the boundary to fight the steel and cast iron. Now, in case of the cast iron also, there are different variants of the cast iron. But in this case, cast iron, molybdenum, nickel are frequently added to improve the hardenability of the cast iron component. And of course, but properties of the cast iron actually decides what way carbon exists within the structure, whether it is a form of a graphite or in the form of a cementite. So that actually decides the structure of the properties of the cast iron. For example, usually you know the three different types of the cast iron: gray cast iron, white cast iron, and the malleable cast iron. In gray cast iron, we are having very low ductility, excellent compressive strength, very good machinability, wear resistance, very good sound and damping characteristics. Because in gray cast iron, this kind of the properties achieve Hello. Should I start? Okay, so actually there's sorry for the discontinuation. So that's why steel making is easily done. Now, most of the steels are classified as per the American Iron and the Steel Institute AISI this thing code. We use it to understand the different types of the steel. For example, the first two digits indicates what are the specific class of the steel and what are the major alloying elements, and the last two digits is basically indicates what are the carbon content. So therefore, we understand the steel is basically a backbone for the modern industry economics, and therefore so many applications we can find out the using the steel. So that's why it's I think very important to understand the different kind of steel making processes. So if you follow the right hand side AISI code, if you see the first two digit 10, simply understand the plain carbon steel, and that means carbon percentage is actually very low. And then we can see the 15, and then it indicates the high manganese carbon steel. Agent depending the unwanted agent, and then once it is done in the first phase, if you see the coal and all this thing, it reach to the blast furnace, and then after that we basic oxygen steel making means here we can making the control alloying of this thing, basic oxygen furnace steel in this case. So first is the iron making, then we try to make the steel making just to control addition of the different alloying elements. So once it is done, furnace, then we put the ladle just to carry this molten steel, and we put the casting unit, that continuous casting unit, and in continuous casting unit, the steel trap or different kind of the semi-finished products we can produce. For example, continuous casting, we can produce the blooms, billets, slab as per the requirement. This type of the thing we can produce. But further, once we produce the semi-finished product, then we follow the different manufacturing operation, mainly the rolling process, metal forming operation, and hot rolling process. Then we can reach the finally the different kind of the product, construction product. So different shape. The pipe in the form of a pipe, in the form of a seat, in the form of a solid bar, the square bar, all this can be done using the rolling operation, or I can say the metal forming operation. So that's why this is a continuous process. So in the steel industry, we can say that we start from the iron ore, limestone. This is the ingredients. Follow it and use the furnace. Then control addition of the alloying elements, steel forms. Then we follow the casting operation, and then produce a semi-finished product. And from the finished product, we follow another rolling operation or the forming operation. Then we reach the final component. So this is the complete cycle of the steel making process. Now, apart from the steel making, there is one single crystal structure sometimes is very important to produce. And this process is actually production of the single crystal structure is usually very costly. It's a more than, I think, cost might be involved more than that of the. Why there is a need the single crystal? Because single crystal means is a uniform and continuous crystal structure throughout the entire material. The single crystal structure exists. That means there might not be any kind of the grain boundary. So no polycrystalline material, no multiple grains will be produced in this particular case. So therefore, So this can be produced in the utmost care for a particular component. And this is very specific because there probably there is no grain boundary, so therefore yield strength might be low, but at the same time, there is a very minimum amount of the creep is possible to achieve in case of the single crystal structure. So that's why very high performance industry, for example, aerospace industry, power generation, and automotive industry, we can use the single crystal structure. Even one example is the turbine blade. Turbine blade, we can say this is single crystal structure. Engine component, where the life might be very high, engine component. So therefore, we try to produce any kind of the polycrystalline structure, and rather we can produce the single crystal structure. There are so many methods to produce the single crystal structure. Few of them are listed here also. But one process I try to look into here, that is called the zone melting method, which is a very simple method also. In this case, how you can produce the single crystal structure? We try to create the liquid zone by melting a small, very small amount of the whole liquid metal by externally heating the this thing by using the lamp. For example, here we're using the lamp. We can heat it and create the small molten zone, and that molten zone can be gradually moved that comply with the moving in the solidification front. So we are not extending the molten zone, rather we can move in such a way that the solidification front move with the same velocity. So therefore, what happens in this case, when a zone melting, very specific zone, we are melting it, and in this case, it is allow manipulation of the distribution of the any impurities or phases within the solid. When you're melting it, the impurities will just segregate it in the. It usually comes to the lighter impurities come to the top surface, heavier impurities come to the bottom surface. So that impurities, basically we are collecting the impurities by melting in the very localized position, particular zone. And then we keep on gradually moving, or we are basically collecting the impurities presence there. And of course, at the same time, we follow the solidification on particular direction. Then we can produce the single crystal structure in this. This is the simplest way to produce, that is called the zone melting method. Now, try to look into the solidification, steel solidification with reference to the equilibrium phase diagram. Try to understand the kind of the steel also here. So steel solidification we perform the when the solidification is basically understand that perform the transformation of the molten metal into the solid state, and when you transform the solid state, the different phases can produce, and the different phases can produce a different kind of microstructure and different properties. Different properties will not too much vary, but of course some variation of the properties must be there depending upon the microstructure we can develop after the solidification in case of the steel industry. For example, this alpha ferrite. Alpha ferrite is basically you understand the solid solution of the carbon in a BCC item. But here the alpha ferrite exists in the very carbon percent. The solubility of the carbon percentage is very, very low. So maximum solubility is only 0.02%, and that also happens at particular temperature. That is the 727 degrees centigrade. That is the eutectoid temperature. We can have the maximum solubility in the delta ferrite. So here it means that very low carbon percentage we can expect kind of the ferrite, alpha ferrite structure. Then gamma austenite structure is the solid solution of the carbon. But in this case, maximum solubility of the carbon in the austenitic structure is 2.14% of the carbon. You can see this zone also, that gamma austenite. Here the carbon maximum solubility of the carbon is 2.14% of the carbon. That creates the austenitic structure, austenitic phase, and that exists over a range of the carbon, and usually in the high temperature zone, the austenitic phase. It is the solid solution, but different phase means this phase exists in the solid phase actually. The maximum solubility of carbon 2.1%, and eutectic temperature, that solubility exists at the eutectic temperature 1147 degrees centigrade. At this particular temperature, the maximum solubility of the carbon exists. But it is not stable below the 727 degrees centigrade, because below 727 degrees centigrade, if carbon percentage is very low, then alpha ferrite is more stable structure. Now, delta ferrite is another single phase structure, but delta ferrite exists at the high temperature phase, and it is also very low carbon percentage. Solubility of carbon percentage is very low, and it's actually stable at the very high temperature around 1394 degrees centigrade, and of course it melts. But this is a solid phase, but it melts at 1538 degrees centigrade. So I mean to say that almost very low carbon percentage, close to 0% of carbon, and it's a below 1538 degrees centigrade. Then delta ferrite structure exists, but below 912 degrees centigrade, then in this case alpha ferrite exists. So both are ferrite phase, but one is the alpha is the low temperature phase, and the delta ferrite is the high temperature phase. Now, if you follow this structure, we can see there is we can produce the eutectoid steel, which is called the pyrrolate structure. In this case, steel composition is the carbon percentage is 0.77%, also known as the 1077 steel. 1077 steel as per AISI index, we can find out the carbon percentage is the 0.77% of carbon. In this case, it actually produces the unique structure that is called the pyrrolate structure. Pyrrolate structure is basically when steel head around 800 degrees centigrade for just 1 or 2 minutes, it will consistent entirely of the austenitic grains. Then when you cool to 27 degrees centigrade, then pyrrolate structure, and holding for 5 to 10 minutes at this particular temperature, the austenitic phase completely transferred to the pyrrolate phase. Pyrrolate grain basically. So pyrrolate grain is not exactly the single phase, but I can say that it's a mixture of the ferrite and cementite phase, that we can say, and they follow certain morphology. So therefore, morphology means basically alternate plates of the ferrite and the cementite exist, and that is known as the pyrrolate structure. These ferrite plates are much more in the pyrrolate, around 90%, but 10% is the cementite phase. So therefore, we can, from the micrograph, we can identify the light phase is the ferrite plates, and the dark, and the cementite plate is the light phase, and but dark phase is the ferrite phase. And of course, in this case, this lamellar structure, the cementite plates are only around 0.1 micrometer thick. So this particular structure exists, which is known as this pyrrolate structure. Now, with respect to the eutectoid composition, the eutectoid steel, we can say the hypo and hyper eutectoid steel. Hypo means below the 0.77% of the carbon, and hyper is the above the 0.77% of the carbon, the steel. So in case of the pure iron, we see the austenitic gradually transferred to the ferrite, cooling when to 912 degrees centigrade, and adding carbon to the iron lowers this temperature. If you lowering the temperature, in this case, the maximum temperature can go up to the eutectoid point. Now, eutectoid point represents the temperature and composition of the phase diagram. A reaction occurs, and the reaction is basically one solid. That means austenitic phase decomposed into the two different phases. One is the ferrite, another is the cementite phase. So therefore, this point is the eutectoid point, and this exists at around 722 degrees centigrade, and carbon percentage is 0.77% of the carbon. And in this case, if it is less than 0.7, it is called the hypo-eutectoid steel. And we can see that ferrite, we have already seen 0.02% of the carbon at the eutectoid temperature, making it easily. Actually, the ferrite structure is almost pure iron because carbon percentage is very, very low. What we can see that things austenite is the, we know this is the another form of the carbon. It can dissolve carbon more than ferrite, but holding austenitic transforms to the pyrrolate structure at 0.77 carbon percentage at this particular temperature, and of course austenitic having the FCC phase, but ferrite is having the BCC phase, BCC structure. So therefore, steel composition, if you look into the 0.4% of the carbon, it means that it's a less than carbon percentage is less than eutectoid composition. So therefore, if it is cooled from the 850 degrees centigrade to room temperature, then what will happen? The different transformation will happen. So in this case, ferrite has formed as a number of alpha grains along the prior austenitic grain boundaries. We can see from the figure also. This is the complete the austenitic phase, and then the ferrite phase is try to form along the grain boundary of the austenitic phase, and then too much of lower the temperature below the 722 degrees centigrade, it creates the pyrrolate phase. and there is a perlite phase along with the ferrite phase. There are specific morphology to try to follow. So therefore, 727 degrees Celsius room temperature, this austenitic grain will completely transform into the perlite grains, which is a combination of the ferrite plus cementite phase. Now, hyper eutectate steel, basically high carbon steel, which is more than 0.778% of the carbon in the steel itself. In this case, increasing the carbon percentage dissolved in the austenitic pushes iron atoms apart. Therefore, try to stress the chemical bond because it tries to absorb more amount of the carbon in this case. And 820 degrees centigrade, we can see around 820 degrees centigrade, the solubility limit of the austenitic phase is around 1% of the carbon. So it means that 1% of carbon can dissolve in the austenitic phase in this particular temperature. So therefore, if you further cool it, then this cementite also having the fixed composition, that is 6.678% of the carbon. Now, when cementite is actually in this particular cementite phase is actually very brittle. So definitely it actually the properties of the steel component, mechanical properties. So now if we look into steel composition around 1% of the carbon, then what will happen is cool from 850 degrees centigrade. And 850 to 760 degrees centigrade, what will happen? The austenitic phase is transforms to the austenitic and cementitic phase. Along the grain boundary, we can produce a cementitic phase. And that is true in case of the hyper eutectate steel. But when the hypo eutectate steel, the grain boundary might be having the ferrite phase usually. Now further cooling, that will drop to the combination of the eutectate phase, that is the 0.778% of the carbon. That means you can perlite structure, and when it's room temperature, then austenitic grains will transform to the perlite phase. It's basically ferrite plus cementite. This is also combination of the ferrite plus cementite. So basically, perlite structure we can say the specific morphology of ferrite and cementite, which is combination of the 0.778% of carbon. But if you hypo or hyper eutectate, it is a combination of the perlite and ferrite, and perlite itself having the ferrite as well as the cementite phase. Both phases are there. Similarly, hyper eutectate also the combination of the ferrite plus perlite plus cementite, or even perlite also having the ferrite plus cementite. So basically, in case of the hypo eutectate steel, the percentage of the ferrite might be low, but in case of the hyper eutectate, ferrite percentage is more in case of the hypo, but hyper the ferrite percentage might be more in this case, less in this case. So that's all. In this case, we try to explain the different kind of this steel structure and steel making process. I think it helps to understand in the better way this particular. So thank you very much for your kind attention. Now, if you have any questions, you can raise this online platform. Thank you. Okay, Mr. Rahul Kumar Sharma, I think you are a little confused to understand what kind of the courses you should do, because it depends on your interest. Actually, if you are really very interested to look into the thermal and the fluid science, you take the different courses. There are so many courses, and I think each and every semester you will be able to get these courses in the NPTEL platform. So as per your interest, or maybe which area you are supposed to work or currently you are working, you take the relevant courses in this particular as per your choice. And of course, NPTEL course will definitely, it helps to understand the subjects in the better way, and you have also free time to look into the different types of the courses, of course. But what I suggest is that take the courses, any courses, if you take any thermal fluid science, any courses, but as per your interest, as per your working area, that definitely it will be helpful. But be serious to study these things, that when it is releasing the video, we just carefully follow the video also, and at the same time try to solve the assignment problem just following the video lectures. So that will helps to develop your skill to understand the subjects in the better way. Once you understand the subjects, then you can apply in any field, maybe in the applications area, maybe in manufacturing area, you can apply. But I believe some basic understanding of these things is required from these courses. Then you go for the application of your understanding to the real world problem. So in that way you can follow. But you can follow any semester, because every semester there are lots of courses that have been floated. But only thing is you have to choose the right courses where your interest is there. Thank you, Rahul, for your questions. If you have any other questions, maybe you can raise it. If you do not have any questions, then I just simply stop here. Okay, so thank you very much for your kind attention.